Hello everyone, in this video we start section 8.4 where we're going to cover, in this video, what's known as the alternating series test. That's on page 64 and 65 of the notes. So the alternating series test we're going to illustrate with an example here, but let's first notice some examples of what are known as alternating series. So an alternating series is simply one that has this minus 1 to the n or n plus 1 or n minus 1 factor in the summand, okay? So if I take like this minus 1 to the n minus 1 and multiply it by 1 over n and take the sum of all of that, this is actually a very special series. It's called the alternating harmonic series, which we'll talk about in just a minute. But this is an example of an alternating series. This one right here is another example of an alternating series. You notice I have this minus 1 to the n factor, and then this other stuff here that comprises the rest of the summand. So here's what the alternating series test says. It says, okay, if you have an alternating series, and you notice that's just, since here we're starting with n equals 1, this power here is n minus 1. So technically you get a minus 1 to the 0, which is just 1. That's why it starts with positive b1. You know, this could, like we see in this example here, start with you know, a negative value. Anyway, so when you have this alternating series, and let's suppose these bn's are positive, and we'll see that it only needs to be eventually positive. We call these bn's the non-alternating part. Well, if these bn's satisfy that they are decreasing and in fact decrease down to 0, then actually the series converges. And let me give you the prototypical example of the alternating series test at work. This first example we're going to look at is the alternating harmonic series. So you see, it looks a lot like the harmonic series. You know, you have 1, 1/2, 1/3, 1/4, but they're not all being added up, right? When they're all added up, we know that that diverges. The harmonic series diverges. But the alternating harmonic series, well, let's see what happens. So the first partial sum is just 1, right? So way over here. The second partial sum is 1 minus 1/2, which is right here, smack in the middle, right? And it's 1/2, which I'll write as 1 minus 1/2. And now I add 1/3 to that. Well, 1/3 is a little bit smaller than 1/2, so I don't go all the way back. I stop maybe around right here. So this is 1 minus 1/2 plus 1/3. Okay. The next thing I do is I now go backwards 1/4 from here. That's how I get the next partial sum. So I don't go all the way back to where I came from. I only go backwards 1/4, so that's maybe like right around here. So 1 minus 1/2 plus 1/3 minus 1/4. Now, the next thing I would do is I would then go backward, or I guess go forwards 1/5, right? And so that would put me maybe right back here. You notice I'm never getting back to the last partial sum that I was at. So this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And now I'm not going to keep writing because I'll run out of room, but I will sort of put the check marks, so or the tick marks. So the next thing I get is all of this, but then minus 1/6. Well, you'll notice this distance here is more than 1/6, so I don't go all the way back to this previous hash mark. So this would be the next one, and then the next one is I add 1/7 back onto that, and then subtract 1/8 from that, then add 1/9. Well, what do we notice about the partial sums? I'll just put dot dot dot, but they seem to be settling somewhere in here. Well, when the partial sums start to settle in one location, that is essentially convergence of the infinite series. So in fact, the alternating harmonic series converges by the alternating series test. And let me show you how you would actually verify that. You're not going to have to draw a number line every single time. Here's how you're going to verify it. First, identify that it's alternating. So it's alternating, check. This is an alternating series. Then identify Bn. Well, in this case, Bn is just 1 over n, right? What is the non-alternating part? The non-alternating part is just 1 over n. Okay, and you can see it if you rewrite the alternating harmonic series like this, right? Notice right here is Bn, this 1 over n here. Okay. Now, once you have identified those two things, you first have to show that the Bn is decreasing. We're going to kind of wave our hands over that. As long as it's clear, you notice 1 over n is always getting smaller as the n value increases. So we're just going to say 1 over n is decreasing. And part 2 says you have to show that the limit as n goes to infinity of 1 over n equals 0. Well, yes, right? that much should be clear. Okay, so then you would say by AST, the alternating harmonic series converges. Right? So this is a super important example, so put a star next to it, highlight it, whatever you want to do. It's a super important example because we know that the harmonic series, if you get rid of this alternating part, the harmonic series diverges, but the alternating harmonic series converges. All right, so now coming down here, let's see what happens here. So we see that it's alternating. The Bn appears to be n over n plus 1, okay? So the first number we get when we plug in n equals 1, our first partial sum is negative 1 over 2. So negative 1/2 is our first partial sum. Now we add on to that to get our second partial sum when n equals 2. So, so it'll be this minus 1/2 plus, now plug in 2, and you get, that's a positive 1 times 2 over 3. So I add 2/3 to this. So minus 1/2 plus 2/3. And now to get my next one, I think you see I'm going to subtract 3/4. Right. And now to go the other, to get the next partial sum, I add 4/5. And now the next one would be back here. The next one would be over here, then over here. And we see the partial sums aren't settling down. And so, in fact, this series here diverges, right? The partial sums are not settling down. Okay, in the next video, we'll go over more of the alternating series stuff from page 65.